Howdy! We're at question number 9 from the 2018 paper. And I classified it as differential calculus. Let's see what it looks like. It's a third order polynomial. And we're given with two turning points. And importantly, we're given the values of the y-intercept and the x-intercept, which is also known as a root. Okay, so in the first question we're asked, well, show that the values of b equals 1, c is that, and d is 20. And these come from this general equation of the third order polynomial, in which you can see there's three unknown values there, b, c, and d. So we're just shown to prove those values. Well, we can use two pieces of information here, possibly. We can use the information on what is known as the turning point. And these would be these points P and R. That's a possibility. However, in this case, we're not really given any information regarding these points. So that rules that out. And we're also given the root values, right? So we're given this value here at -5. So we can also use the intercepts to determine these unknown values, and that's exactly what this example calls for. So by intercept, what I mean is where it crosses, where the graph crosses specifically the x-axis. Because I know that if I know these values, this function g of x can be simplified by means of factorization, right? And so typically a third order polynomial can be factorized into 3 terms, each containing an x in the first instance. But I can also write this down slightly less simplified as a first order term multiplied by a second order term, right? And this is exactly what's happening in this example. And the reason for that is that, well, I'm given the intercept on the x-axis, so I can already complete this first order term. That's just x plus 5, because I know it cuts or it crosses the x-axis at the point -5. And then another important thing is, well, I know that it touches the x-axis at P, it doesn't cross it. And in that instance, you can use a special equation for the polynomial or the second order polynomial. And the two instances I've drawn in here correspond to this convex nature of this curve. When it touches the x-axis on the positive value or the positive side at a random point A, this polynomials or this the second order polynomials equation can be written as x minus a to the power squared. And when it crosses the positive or the negative x-axis, or when it touches the negative x-axis, it can be written as x to the plus a to the power of 2. Okay, so what I've put here in these little black box, in this little black box here, is really a special case. And when you know this and you realize that, then you really get to solve this equation or this question quite quickly. So we have this x plus 5. That's very easy, and it's read off the graph as I said here. But we also have this very special case in which we know the form of that. So that's going to be x minus, and because I don't know the value on the x-axis, I'm going to use the point or the constant k, and I know that's to the power of 2. Okay, so I've already got the form and some pieces of the information of this function g, but my task now is to solve this k, which is unknown. Well, that becomes easy because I'm given another point on this graph. And I know the value of this function g in the point x0 is 20. So 20, when x is 0 here, is 5 multiplied by minus k to the power of 2. Okay, solving this then, you find that k squared equals 4. And solving that further then is, well, k is plus or minus 2. And because k on the x is on the positive x-axis, only one solution counts. And so I know k is 2. Okay. And then the final step, what I have to do is I have to just multiply out these equations or these specific terms of this function g so that I get it into this general form and I can solve the values of b, c, and d individually. So let's do that together. That's x minus 2 to the power of 2. Okay. What I'm going to do is first just multiply out quickly this second term. So I'm keeping the first term. That'll be x squared minus 2 times 2 is 4x. And 2 squared is 4. Okay, and now I have to multiply each of the terms in this bracket with each of the terms in that bracket. And if you do that, you get exactly the equation in this form, that gx equals x to the power of 3 plus x squared. So b is 1. Okay. Minus 16x. So c is minus 16 and plus 20. Okay. And so d is 20. And that's fine. That's the answer to the question. But it all hinges upon this graph here, and that you realize that when you use these roots or these intercepts, when it doesn't cross the x-axis, the parabola has a special form. Okay, that was question 1. And then question 2, well, now they want to know the coordinates of this point P of R and P. Well, we've already spent quite a lot of time on this point now, because we knew it was a special turning point. And we've calculated the value of that point to be 2, right? Remember that? So I know already from my previous calculations in 1 that P has an x coordinate of 2 and a y coordinate of 0. Okay, and now for R, well, R also has a very unique property in the sense that it's a turning point. What do I know at a turning point? Well, I know that the slope, I'm going to write this down, slope at a turning point equals 0. Okay, so what do I need to do? I need to, in the first step, calculate the derivative, so g prime of x. I need to equate that to 0, and then I solve for x. Okay, so let's do that. My g, let's just first write the general form of g so that I just have it here. That was x to the power of 3 plus x squared minus 16x plus 20. Okay, I'm deriving it, so I'm writing g prime of x, that equals 3x squared minus 2x. I apologize, something really strange happened there. Okay, minus 2x minus 16. Very easy derivative to calculate, right? And the slope at that turning point is 0, so I can equate that to 0. Now it's nothing more than solving a second order polynomial, okay, or a parabola. I know I have to factorize it. In the first term here, I get 3x, and the second term I get x. Now my homework is to write down the factors of 16. I know 16 can be multiplied by 1. That's one option. 8 can be multiplied by 2 to give you 16. That's a second option. And 4 can be multiplied by 4 to give you 16. I have no idea what to use at this stage. I went ahead and first tried 4 and 4. I know that the one has to be positive and another one negative, because I have to get minus 16. And what I saw is that gives me something that's not correct, so I just left that out. And then sort of by process of elimination, I knew that that wasn't the solution. Okay, I went to the next trial and I wrote down 8. Let me just see, 8 and 8 and 2. Okay, so those are multiples of 16. Remember now, I have to get minus 2 here. So if I have minus 8 plus 2 here, maybe that's something. We can go and test that on the side here, multiplying each term in each bracket with one another. And I get 3x squared plus 6x minus 8x minus 16. And that gives me minus 2x. So I know this factorization is correct. Okay, so the value therefore of the x coordinate of the point R is therefore, because we've already calculated this one, I think. Did I do that correctly? No, I didn't. That was also wrong. Minus 2. Oh goodness, there's a mistake somewhere, I think. It has to be plus 2. Oh, big mistake. There. Okay. So these signs have to be turned around. Okay, let me do. See how easy you make a mistake? So it has to be plus 2, so that has to be plus 8 minus 2. Carrying that over, that has to be plus 8 minus 6, and that's plus 2x. Now it's correct. Okay, so we have the value here of x equals 2, and that was associated to the point P, right, that we had already. And so the x value associated to the point R, well, x equals minus 8 over 3. Okay. What we have to do now is calculate the corresponding y coordinate. How do we do that? Well, we just plug in minus 8 over 3 into this general equation of gx. So I calculate here g of minus 8 over 3. And that is 1,372 over 27. And so the coordinates of R is minus 3 over 8 and 1,372 over 27. Cool.